now we are very happy to have Johan Henriksson. He will tell us about spectrum continuity and level repulsion in the Ising CFT.
Okay, well, thank you very much for the introduction, and also to the organizers for inviting me to speak here. It's great to come back in person in these workshops. So what I'm going to talk about today is some work in progress that we have together with Stefanos Kosmos, who's a fellow postdoc with me at PISA, and then Martin Rehost, who just met in the previous talk. And we're currently finishing this paper. And since there are many very knowledgeable people in the audience, any comments or suggestions would be very appreciated. So as the title suggests, one topic of our paper is this idea of level repulsion. So first I wanted to say some general comments on that, and then move on to discuss the case of the Ising CFT and our study, and then I'll move to the slides to present some results. So what's this level repulsion? Well, there is a famous result in quantum mechanics, which is called the von Neumann Wigner non-crossing rule. Or also known as voided crossing or level repulsion. And it's in the context of a quantum system where we have a Hamiltonian that depends on a continuous parameter, so say H0 plus GH1 in a simple case. And if you take such a Hamiltonian and you make a plot over the energy levels, so G, P, you typically find a picture looking a bit like this. So the statement of this non-crossing rule is that generically as this parameter G varies, eigenvalues do not cross or collide. And sometimes you can even play a game and you can generate two random Hermitian matrices and make plots like this. Sometimes you find that it looks like they're coming very close to each other, but then when you zoom in, you will see that they go away, almost like a hyperbola. And the kind of simple argument for why this happens is you can leak even in a 2x2 case. So say a matrix, say E minus delta, A plus BI, A minus BI, E plus delta. This is the most general 2x2 matrix. And to make the eigenvalues of this matrix coincide, you would need to tune three real parameters, delta, A, and B. And if you only have access to one, in this generic case, you would expect that you would never have two coinciding eigenvalues. And in fact, if you have a quantum system with three parameters, for instance, if you have a triatomic molecule when you have two distances and one angle, in fact you can make two levels exactly coincide. So there is an exception for this rule. And it's if you have some additional symmetry that divides the Hamiltonian into different sectors, where essentially its off-diagonal entries are automatically zeroed. So states in different symmetry irreps may cross. So in our work we were interested in a more general question: what happens in the context of a conformal field theory? So say you have a CFT that depends continuously on some parameter, the marginal coupling constant, and what would happen? We would expect to see a similar non-crossing behavior and other features that come with the idea of a spectrum that depends continuously with this parameter. So what's the equivalent to the Hamiltonian in a CFT? Well, the best equivalence is the dilatation operator, and by the conformal mapping of the plane to the cylinder, in fact the plane dilatation maps exactly to the Hamiltonian of time evolution along the cylinder. And by this kind of exception case here, we should divide the CFT spectrum as, say, a formal sum over all representations, say, of some global symmetry group and some Lorentz group. And then inside each such sector, we should look at the spectrum of the dilatation operator.
Are you able to make this analogy precise?
This,
meaning that, okay, in the case of quantum mechanics, this Hamiltonian acts on some space, which is the same space for all family of Hamiltonians, and then it's just the matrix varies.
yeah. And here it's an infinite dimensional system.
Well, in the case of CFTs, this dilatation operator acts on a space, but this space is different for each CFT, it's its own space.
Yeah.
So this makes the analogy not precise. Can you make it more precise, or is it just an analogy which...
I think it's, our point of view is really this is an analogy, and we want to test, do we even have a similar system in, well, more generally in a generic CFT, and then in practice in the CFT that we want to study.
I think one can say a little more, right? There's several papers that study this notion of parallel transport on the space of CFTs, both in 2-dimension, higher dimensions. So indeed, there's
I think you're on.
You need to introduce a connection, otherwise, as Slav is saying, you really cannot compare the state space on one point to the conformal to another point. They're different. So you need some notion of how you parallel transport to compare them.
Mm-hmm. Yeah, and I think you're even on better footing where you actually have a coupling constant inside the conformal manifold. But as we're gonna, jumping a little bit ahead, we're gonna look at the Ising CFT moving between different space-time dimensions even. So I would say it's not completely guaranteed that we're gonna see this. And part of our study is to see if it's really possible to observe such phenomena. So what's the kind of scenario that we might be looking for? So inside delta, inside each such symmetry sector, we can again make some function of the coupling, and say you know the spectrum at zero coupling, and then maybe even there are two operators starting from the same point here, and then we expect as you increase the coupling, maybe two lines go like this, naively, and what we would see if we indeed observe such level repulsion would be that these kind of get closer and then repel. And a model for this involving just these two operators would be if we write the dilatation operator as a 2x2 matrix, say delta 1 of G, delta 2 of G on the diagonal, and then some other functions x of diagonal, where in principle this x could also depend on the coupling. And here, so this delta 1 and delta 2 represents these dashed lines, and then you want to solve for the eigenvalues of this matrix. So delta plus minus is delta 1 plus delta 2 over 2 plus minus square root of delta 1 minus delta 2 over 2 squared plus x squared. And these are the solid solid curves here, so delta plus. So as we already discussed, the kind of a general question in our work is that can we see evidence for non-crossing in CFT?
Sorry,
Yeah.
you mean when you are very close to these crossing points, maybe your Hamiltonian can be approximated by this two-level system?
Yeah.
What's the reason behind that?
So this is already ignoring this line, right?
Yeah.
So in general, you would expect a larger matrix, of course. And as long as, say you're in some intermediate point here, as long as all the diagonal elements are well separated, and as long as the off-diagonal elements are small, then the eigenvalues are very, very close to the diagonal elements. And as long as, and by the same logic, you can kind of separate away the, say, the third operator when you just analyze the behavior here. But strictly speaking, you need to diagonalize the whole matrix. So before you start complaining now, I need to tell you some exceptions where we don't expect this to happen at all. And one of them is as already in this picture, actually when the coupling constant goes to 0. Where if you take this kind of approach, really everything just simultaneously is tuned down to 0, so we kind of lose this generically part of the statement. But we also expect this to break down in the case where we have an infinite dimensional symmetry. So for instance in a 2D CFT or in the planar limit of say n equals 4 superdiagonals. So there's actually a very nice paper which already discusses this case, which I thought I should briefly mention. So the example, this is called Chemsky 2015, which exactly discusses n equals 4 super young males with gauge group SUM. So if you don't know much about this theory, don't worry. The kind of only important property we need is that there is a planar limit in the theory, an expansion for large n, where you can write down the operator dimensions as a function of some constant, coupling constant lambda as a series in 1 over n. So having a 0 order term plus 1 over n squared delta 1. So this lambda is g square young mils times n. This is total coupling. And these leading order terms, for many operators in the theory, can be computed exactly using integrability methods. And specifically, you can compute them to arbitrary, at least some operators to arbitrary precision numerically, or you can extend some expansions at strong and weak coupling using integrability. So the case I want to discuss here is just the spectrum of singlets, so R symmetry singlets, and spin 0. And then you get a picture looking something like this. So here we have this lambda, and the two interesting operators are the ones starting at dimension 2, delta here, and dimension 4. And the operator at 2 has some non-trivial dimension depending on lambda, which keeps growing like this. And it's called the Konishi operator. And this delta naught of Konishi again can be determined numerically for any coupling, and it has a weak coupling expansion 2 plus 3 lambda over 4 pi square. And a strong coupling is grows to the power lambda to the 1/4. So 2 lambda to the 1/4 minus 2. So lambda goes 0 and lambda goes infinity level. Then there is the next operator, which comes out from 4, and in fact stays at 4 for any value of lambda. So let's call that O. So it's a double trace operator. It has dimension 4 in the planar limit, so it has a 1/n correction as well. And then in fact there are 3 other operators starting here, but they're not important for us. So this is the picture at infinite n in the planar limit where the non-crossing rule breaks down. But then as soon as you go to finite n, you expect that these two curves develop a finite separation. And in this case, this model is kind of working very well, because you can really think of this as the basis of operators in the planar limit. And the diagonal entries are these delta zeros. And x here is parametrically small in n. So it can be seen that this x here, which actually determines the separation, the smallest separation is 2x, goes as 1/n. And so the precise constant here cannot be determined currently, but what you can do, and what was also discussed in this paper, is that you can kind of go further up here, where the Konishi operator keeps encountering new operators, double trace operators of this type, and ultimately hit operators of dimension 2j. And then you can use some holographic results to actually determine the coefficient in front here. Yeah.
Well, I'm not sure. Perhaps it can be determined, but we know the abstract meaning of, as far as I remember, in Grisha's paper. He told what this coefficient x should be. It should be a certain OP coefficient, and perhaps we don't know the value, but he was more specific than what he wrote there.
Yeah. There's a whole discussion in this paper.
Yeah.
That's a good point. And part of this discussion depends on the fact that you have a 1/n expansion with only even powers of n squared. Yeah, so you can relate this to a certain OP coefficient that you expect to see in the involved operators, indeed. And then the nice thing is that if you also go to large value of this integer j, which means that you really move into the strong coupling region, you can use some holographic results by Minahan and Pereira to even get the coefficient in front of this 1/n. But you're right, they're related to some OP coefficients in the theory.
Sorry, maybe it's not related to the rest of the talk, and then there's no point. But how do you see it's even 1/n? What's the argument for the scaling being 1/n?
So the argument for the scaling 1/n is that it relies on the fact that these dimensions, the naive dimensions have a 1/n square expansion, and then also the correlators, etc., also have a 1/n square expansion. But then in order to to resolve these while keeping the 1 over n square expansion, you need to pick up some kind of square root of that in the separation.
It's just the amplitude of a massive stream will decay to a pair of gravitons.
Well, that's the holographic argument. But okay, without appealing to holography, you can still make an argument when you tie down exactly all the involved quantities and also involved OP coefficients. Yeah, I didn't want to go into the details of that story. And then, yeah, from holography, it's kind of clear that you should have this. And in fact, explicitly known in the large lambda limit. But this region, you might argue, this is something like lambda equals 40 or something. So
Yeah, that's fine.
so it's a bit far from holography, whereas holography should work further up. Okay, maybe lambda 40 is big enough for holography. I don't know.
I think if you just want a simple example, I mean, you didn't really care specifically about n equals 4 reading notes here. If you just want a simple example, you can just write down a very simple holographic Lagrangian, and it'll be an exact example of your dilatation operator you've written up there. Write down the quadratic action interval for two scalar fields with some diagonal term as your.
Yeah.
Okay.
Let me just mention why am I asking this? Because in of course everything is 1 over n, but to any order in perturbation theory, these operators don't mix with each other, right? So if you start doing perturbation theory at weak coupling, say, to any order you would expand at weak coupling, they will never mix. 2 and 4 are always separate. So from that point of view, I would expect this gap to be exponentially small.
So I think if you do perturbation theory, order by order, you will find some dilatation operator which is kind of block diagonal within the operators with the same dimension here, right? But in theory, you don't have any control over these
No, you do.
of block diagonal entries.
No, you do, of course.
Okay, you can compute them, or are they always
You can compute them, but they are expected to be exponentially small.
They are exponentially in the coupling, yes.
Yeah.
Yeah, but then you go to finite coupling.
Maybe I can suggest a resolution to this. I think this delta 1, like the 1 over n squared correction, like as a function of lambda, will have poles at these intersections.
Oh yeah.
So
Yeah, if you know this, and in fact you do in some of these from strong coupling, again working up here, you can really see poles where that's how he.
Yeah, but what I'm saying is that perturbation, because there are poles, the perturbation theory it cannot converge at that point.
I think
But you don't see these poles at weak coupling.
But there are no poles. It's
You-
not
you
for
don't
the
see
delta,
that
it's for the
coupling.
3-point function that you have poles. You have poles for the 3-point function, not for the dimension.
No, I'm talking about this delta 1 of lambda, this function of lambda. I'm saying it will have a pole at this intersection. If you knew it as a
Are you
function.
sure?
Yeah, but
I don't think so.
that's not from weak coupling. That's from strong coupling, right?
I'm just saying this is a general statement, but this picture to be true, because you're saying at the intersection, the splitting will eventually be order 1 over n, right? For this to be
Yeah.
true, this has to have a pole.
Yeah.
Okay, we can continue
No.
discussing this.
No, the discussion in
But-
Grisha's paper was that the 3-point function needs to have a pole because at the crossing points you need to change between a 3-point function which is of order 1 to one that scales differently with n. But here you don't need that, so I don't think you need a pole. I don't think you expect to have a pole in this.
I think.
Oh, I don't want to hear all the talk.
No, if I remember correctly, I think
Wait,
also
where is the
this
pole?
gets
Where is
a
the pole?
pole.
No, where is the pole? There's nothing blowing up. Everything is fine out there. Where is the pole?
So you have this expansion, and the first correction is 1 over n squared, but when the levels resolve, it should be 1 over n. So clearly the two are inconsistent. You can write very simple models where this happens, and the resolution is that 1 over n squared term has a pole in lambda.
I think it's fair to say that this example will not play any role in.
Yeah.
Yeah, and even no, actually, I'm enjoying the discussion. So yeah, don't worry.
I think a little bit more relevant than this n equals 4 would be Conrad's work. Yeah.
Yeah. Okay. Can you remind?
So Conrad set up this abstract framework for in a toy model, but the idea is more general. Maybe you should.
Okay, yeah, so I was considering
considering a bunch of operators, a bunch of operator trajectories, which are functions of some coupling constant. And there's no particular model. We don't know. We don't have to know a CFT where there's a single coupling constant, like a single marginal operator. But you can use conformal perturbation theory to say, what does a dimension shift by? What does an OBE coefficient shift by? And then, since the operator is exactly marginal, these give you differential equations. So, yeah, delta for some dimension is something computable times delta g. You divide by delta g, so you have derivatives of the scaling dimension with respect to the coupling is some function, and you get a dynamical system.
It's a way of setting up conformal perturbation theory in abstract CFT language.
Okay. Yeah, maybe we should move on.
So if you don't know that work, you should,
Yeah.
when before since your paper is in preparation, you should also take a look.
Yeah.
Because it gives a proof. So Grisha's paper, it wasn't really a proof that level crossing it should not happen. He kind of said, okay, level crossing should not happen, and for this to not to happen, certain things should be the case.
Yeah. Well, our paper is not a proof either.
He had a great intuition. So Connor's work can be viewed as a proof at the level of conformal perturbation theory that in case of a conformal manifold, level crossing does not happen.
Also at finite distance.
Also at finite
Okay.
distance,
Nice. Yeah.
in his toy model example, according
Okay. Good. Yeah. We should discuss it. Sounds good. By the way, another comment to say is that in this holographic setting, you do have control over these x's, and they are indeed small. And in the work here, we really want to just think of this as a model for what can happen, but instead we want to go out and see if we can explicitly observe this phenomenon to happen using the bootstrap. So in our work we look at the Ising CFT, and instead of lambda we're gonna have the epsilon, which is the epsilon expansion, so 4 minus d, and we want to use the bootstrap with this navigator method. So with navigator plus the extremal functional method. And again, I would say we're on slightly less solid ground here, because now we're continuing between different space-time dimensions rather than being, say, on a conformal manifold. So it's not even clear that the spectrum would be continuous. So that's one of the questions we ask. So is spectrum, or even the whole spectrum, or maybe only part of the spectrum, continuous in D? And a related question is then, do operators repel as expected, or maybe they annihilate, they get closer to each other, annihilate, or they somehow, by some other mechanism, decouple as we vary the space-time D. And then if they repel, is this model, so now delta 1 of epsilon, x, delta 2 of epsilon, a good model?
Sorry, can I ask something?
Yeah.
In the bootstrap, when people do this dimensions not integer, you are still imposing unitarity, right?
Yeah.
But generically, we don't expect the theory to be unitary, so will you not find repulsion just because of the nature of the problem you are solving, that you are putting unitarity, so you have some Hermitian matrices? But what will be the physics of that compared to the physics of some real, in quotation marks, epsilon expansion?
Good. So I wanted to comment. So you're mentioning this this work, which was by Slava and Matthias and Balt. He really said that actually, if you go to non-integer dimensions, the theory is not unitary, and in fact that causes a problem both for the bootstrap but also for the idea of level repulsion. But then they also observed that these non-unitarities happen really high up in the spectrum, and which means that the bootstrap appears to work. Maybe if you increase precision enough, it will start breaking down. And
I would say unitarities happen in the spectrum near 4 dimensions, but you don't really know what happens.
No, but at least you can't say unitarity is guaranteed away from integer dimensions.
No, that's for sure.
Yeah. Which means that this opens up the possibility for operators to annihilate, for instance, and not just repel, as we were expecting in a unitary CFT.
For example, I would expect that as you approach 2 dimensions from above, all sorts of crazy things are going to happen.
Yeah. Yeah. So in this work, we're actually focusing between 3 and 4 dimensions, but later we want to study also the limit to D, and there are already some previous studies.
Sorry, but I'm just confused because it looks to me like if you use the bootstrap, by definition you will have level repulsion and so on because you are inputting that you are in the domain of unitary matrices, etc. So can you really answer the middle question of what happens in reality about all these things about annihilation, decoupling, etc. If by hand you are putting in this unitarity that is not there.
Okay, it's a good. I see your point now. Yeah. So the point is, if we kind of already impose unitarity, wouldn't that mean that we start seeing features that maybe aren't there physically? Yeah, it's a good point, and we can't exclude this possibility. I would expect that you would see things starting to go wrong, and you would kind of discover such behavior by maybe the bootstrap problem is breaking down. Maybe you don't even find any allowed points anymore. Yeah.
One comment with respect to this question is that the non-unitarities appear that operators that are not the operators we're going to study, and more specifically in the OBE coefficient. So for this precise problem, maybe what you say is true, but probably not. Like, I don't think it's going to affect the result. Like, it was much higher operators, which were quote-unquote unphysical.
Yeah. But maybe the operators we're going to study will annihilate.
Right, we cannot exclude
But then
it,
I would expect that we see it as a breakdown of the whole algorithm.
I mean, you are interpolating between dimensions, right?
Yeah.
And you could have many curves. You could have the physical curve, what you will do if you really change dimensions, and you can have the bootstrap curve that has the same endpoints, but along the way it's just unphysical, and you should not trust the results.
In that
and
sense,
I think it's more likely that it's the last one, right? So
in that sense, we're following the bootstrap curve. That's true. But so let me mention some previous works. Because some of these previous works actually indicate that at least part of the spectrum is continuously down and meeting the 2D Ising CFT, which is expected in 2D. So there is first a paper by Shok.
Maybe I can say something. I think that if we were sensitive to this non-unitarity, I don't think it would be clear that there is this other curve, that it would exist, the other curve that you don't know. I would expect there to just not be any solution at all. And instead what you see is that there is a solution, and it's probably because the operators, you're not sensitive to the operators that are non-unitary, because already operators that appear in that kind of dimension, they also don't show it in the extreme functional method. It seems to be a region that you're not that sensitive to. But of course you have to keep your eye out.
But I mean, this cannot be an exact statement, right? That eventually it will have to enter the non-unitary.
Yeah. I think many of our statements need to be little asterisks sitting next to them. We're not doing rigorous mathematics. We're exploring it in a sense, and we want to see. Well, at first we don't even know okay, we have some idea what we expect to see, that we're going into the unknown.
But sorry,
Yeah?
I'm getting a bit lost. Can I ask a question to Pedro probably? I did not understand what is the, if there is a really strict connection between bootstrap assumptions and absence of level crossing. This seems very strong. Like for instance, there are perfectly fine CFTs like n equal infinity, which would solve crossing, so would be okay with the bootstrap, but would have crossing. So why did you say that inputting positivity would immediately tell you that there is no level crossing?
I was just saying that the curve that we do in the numerical bootstrap and the real curve that we would compute if we were to compute it in non-integer dimensions are a priori not the same curves, right? And we are after very small effects and very small effects of level splitting and so on. And it's just not obvious to me that
I'm not sure if this effect is very, the non-unitarity effect is very small. The level crossing effect is not very small. Well, we will see.
I have a question about, so in the non-integer dimensions here, when you say you might have to relax symmetry, is there some axiom to replace the usual CFT axioms in that case, at least conjecturally?
Conjecturally, I wouldn't know. The point is, part of these previous studies, I'm going to say that they were in fact able to see numerical features using the usual rules of the bootstrap, assume unitarity, with the precision available.
Well, we know which actions we need to relax. You have to assume that the operators have complex scaling dimensions, and we have to assume that the coefficients are in general complex. That's what we need to relax.
Yeah, but that's still non-trivial. But you say under that assumption is to believe that you still have the usual notion of locality and all that.
That's believed.
Okay.
At least I believe it.
Yeah. Okay. Even such questions can be discussed, right?
It's very hard to do so.
Yeah.
But to answer Peter's question, so in fact the non-unitarity in this problem affects, I believe it's to be exponentially suppressed by e to the minus 23, where 23 is the first operator for which has a negative norm when you start analytically continuing from 4 to 4 minus epsilon.
That's near 4 dimensions.
That's
Wouldn't
near
you expect as you approach 2 dimensions or sorts of crazy things?
Yeah, but if you approach 2 dimensions, it could be other crazy things. But around 3 dimensions, I think that.
Sorry, can you give a number to compare with that e to the minus 23?
Oh, so there was this the paper by Slava and
No,
Matthias.
I mean, can you give a number from Bootstrap on the repulsion?
Oh, the repulsion we're looking for is happening at dimension around 7. So, I'll get there, hopefully. So these authors, many of them in the room, they found, they looked at dimensions between 2 and 4, and they find a family of kinks, which match well with the epsilon expansion and interpolated via the 3D Ising to the 2D Ising model. So they found some delta sigma of D, not in closed form, but and delta epsilon of D for values intermediate D. So that's an important idea, despite this later paper that said that CFT is non-integer dimensions is unitary, non-unitary. Then another paper for important paper for our study is the one that Martin already mentioned, which is David Simon Stuffin. Which extracted a quite large proportion of the spectrum for the 3D Ising. And then I want to mention a paper by Capelli, Maffi, and Okuda, 2018, So this was only 3D, this was in intermediate, and they also worked in intermediate dimensions. And they used the extremal functional method at the position of the kinks in the sigma correlator bootstrap. And they extracted a little bit larger proportion of the spectrum, so they got delta epsilon prime at various values of D, and also a bunch of spinning operators. And the main point of their paper was actually to study what happens to the properties for CFT in high dimensions, like twist additivity and Regge families when you approach 2D, which instead should have zero-zero symmetry. So that's why they focus on spinning operators. So the combined picture of these works so far, if we now focus on the spectrum of Z2-even operators of spin 0, so delta, and then D here, so D goes from 2 to 4, let's make a line here. So the first operator is delta epsilon, is epsilon here, and in 4D, the Ising CFT becomes the free theory and it connects to the phi square operator. And then in 2D, it's the epsilon operator with non-dimension 1. And then from the first study, there is a family of intermediate results that in 3D connect to this non-value 1.41. And then from this last paper here, we also learned what happens to the next operator, which is phi to the 4 operator. Let me dash here. Line dimension equals 4. So what happens is it also connects properly to 4D, and that turns in like this. And it goes through the point here, 3.83. And then finally from David Simon-Stuffin's study, he extracted the spectrum of many operators. So he saw these two, and then also the next two, one of which Martin already discussed. We're now somewhere here, two quite close to each other, like 6.9 and 7.3. And then you can also further study operators in the epsilon expansion. So the next operator you expect is phi to the 6. And it has quite large first order anomalous dimensions, so something like this. And then if you go further up to dimension 8, there are actually two operators starting from here. One of them is on the schematic form box square phi to the 4. And that means it's an operator with 4 derivatives and 4 fields. And you need to distribute these derivatives in order to make the primary. And then there is the phi to the 8 operator, which again has a large positive first order anomalous dimensions. So this is, yeah?
Is there an operator box phi squared?
No, they're actually, okay. So these are, all of these, not even that, but all of these are in a way schematic names. And in order to properly, so you construct them out of free operators and you do some renormalization. And if you do this higher order in epsilon, you need to involve stuff like box phi square. So this operator properly has a component along box phi square also.
It's not independent because of the equations of motion.
Yeah.
What about the box phi to the 4?
Box phi to the 4, there is no way to construct such an operator to make it a primary.
But d mu phi.
And box phi square, in a way, you can relate with the equations of motion to phi to the 4.
That's what I mean with box phi square. Why is it, which equation, d mu phi.
The scalar primary.
Is not a primary?
Sorry?
D mu phi.
Well, one of them will be a descendant, and the other one will inmix with this guy.
d mu phi, because of the derivative is the same as phi box phi. Can you comment on the fact that you can't build primary with 2 derivatives and 4 pi's?
Yeah. Okay, very much side remark. So if you have 4 phi's and 2 derivatives.
Yeah, because applications of motion it's about derivatives.
Yeah, so you have 2 derivatives, so you have lost the d mu phi, right?
Yeah, they don't have to.
So either if they act on the same one, you can exchange them with the equation of motion, and you're gonna need to relate it to phi to the 6.
Okay, if not,
And if not, you can always write them as this acting on phi to the 4. So it's a descendant of phi to the 4. If you go to ON, so general n, when you have a vector index also, there is another operator here, which is something like Fox, say phi I, well, phi j, phi j, when you have 2 different types of fields. So I'll say something more about this spectrum actually when I show the slides. So now I want to go on to the slides, so let me just say more or less in words what we did. So we took a bunch of dimensions between 3 and 4, spaced at point 1, and we did a lambda equals 30 study. We had the 3 correlator, sigma, sigma, sigma.
So you just consider Z2 event sector.
Wait. This plot is just a set to even sector, spin 0. But you can make similar plots and also look at similar perturbative data in other sectors. Yes. And we put some standard gap assumptions, and we use the EFM. So use the navigator, and first to locate an allowed point, and then we also went to the navigator minimum inside the allowed region, and we used the external functional method at this navigator minimum.
So what's the role of navigator for you?
So there are 2 roles of navigator. One is to find an allowed point to go, and which is quite difficult because when you're really close to 4D, these islands become extremely tiny. And the second role is that, and we checked this in 3D, that it was reasonable to do this, because it gave agreement with David's results, that instead of sampling, instead of mapping out the boundary of the allowed region, we had the idea that the navigator minimum would be kind of, in a way, the best point to extract the spectrum at. And then you can also look at previous navigator point and see that the spectrum doesn't change much over the last few points. Okay, can we get the projector going? And in the meantime, I just want to say that so we're gonna have some plots, not only for the set to even spin 0 sector, but also other sectors. But for today, I want to focus on this point.
It's all right.
Yeah, and it's also starting up here. Nice. So first, let me just say a little bit more about the perturbative spectrum and give some appropriate references. So again, these are the first 6 operators in the set to even spin 0 sector with their schematic names and what's known about their scaling dimensions. So firstly, phi square and phi to the 4 are the standard ones studied also by, they have a long history, but even the most recent results, epsilon to the 7, are quite recent, by Oliver Schnetz. Then there are these pure power operators, even though we don't know they have some in mixing at higher order renormalization. And they were computed in the 90s by Derkachov and Manashov to epsilon square. And they have this interesting property. They have very large first order anomalous dimensions and even larger negative second order ones. So they're not really well behaved in perturbation theory. And then we have these operators involving derivatives. And they can be computed with a systematic method of Klein and Wegener, or also by the method of actually the same paper who discussed unitarity violation. So I computed a few more of these operators. We also did a recent work on correlators in the epsilon expansion using the inversion formula, where we could confirm some of these anomalous dimensions. And here I'm just flashing from working with the Ising and Owen models for a while. I got a bit frustrated of all the results being scattered across a big body of literature. So earlier this year I tried to collect everything that's known perturbatively about the Owen CFT in this paper. So if you want to play with such...
Do you get many references, complaints?
Not too many, but please keep sending.
Because people are all dead.
Okay. Don't tell Oliver Schnetz that he's dead. Okay, I submitted it to the journal, but I guess if you have more suggestions, please shoot. Okay, so let's look at our results. So here is the results from our study of the set to even operators. And here I'm just plotting the spectrum we get at the different dimensions. And already here you can see some nice things. That the number of operators, the number of zeros in the external functional, seems to be somewhat stable across dimensions. There are some more peculiar things happening in some of the other plots, but this one looks particularly nice. And in fact, it was good because we wanted to study these, the third and the fourth operator, because as you could see, they look like they might be involved in some mixing. Unfortunately, we didn't see it here, and that's why we're later going to try to extend it below 3D. But they all look kind of nice and stable, and they approach these even integer dimensions when you go to 4D. And then we can, as a little benchmark, compare with David Simmons-Duffin's numerical study in 3D. So again, you can see that the counting, the ordering of operators seems to work pretty well, and all these stable operators, these orange circles that he found, seem to continue well across dimensions. On the other hand, you can see he had a different precision. He had actually higher precision. And you can see his values are a little bit systematically below ours. So you shouldn't really stare blind at the exact decimal points of all these numbers, but think of this as still an approximate picture of how the true spectrum might look like.
The deviation starts getting...
The deviation starts getting worse higher up, yes.
Yeah, but who do you think is correct there?
I think this he's probably a bit closer to the true value, because that's also why I asked Martin if he actually has a rigorous bound on the third one. Here, I think even he might be a bit away from the real value, and I think it might continue to shoot down a little bit more with increased precision. But then it's also known that higher up, the external functional method is starting to miss operators, which I'll get to in a moment, actually. So we can also compare with this perturbative expansion. So here I just took the data in the previous table, truncated to order epsilon, and plotted them as lines. And then I did different colors based on the operator content, if you want, of these operators. So the blue one here is phi square, and then all operators with 4 fields are in yellow, etc. And again, we see, so there's especially the third operator here, which had this quite unstable behavior with the terms in the expansion, is deviating a little bit. But we still get quite good agreement perturbatively.
This is just the one.
This is the one loop result. Yes. So we don't expect it to be exact.
Well, far from this.
Yeah. So it actually works better than we expected in a way. Like if you look at these lines here, they follow surprisingly well the one loop.
Sorry, but I'm confused. At 8, for example, where are the missing points close to 8?
Yeah. Here?
Yeah.
Yes, that's the next thing I wanted to talk about. So
Did you try going down to 2 and see what happens?
we have a few points below 3, but so far I think we're so Martin might be running some numerics still, but we might postpone it to a later study, because I think we might need a maybe tighter sampling as well, closer to 2, if you really want to investigate what happens there. It's a direction for the future. Good. So 5 to the 8, why is it missing? Or why does it look like 5 to the 8 is missing? So that's one of the things I want to discuss. And it's known that the external functional method is not perfect. And typically what happens is that, okay, let me move to the next slide. So what does it try to do? In a way, it's trying to solve or approximate the crossing equation with a finite number of operators. And typically, you get an output which matches somewhat well with the expected spectrum at small scaling dimensions. And then higher up, you get some operators somewhat evenly spaced, a bit randomly distributed. So at some point, there must be the first missing operator. So we can try to think what would characterize such first missing operator. And it would be an operator which has, it's not very important in solving the crossing equation. So importance in this case means OPE coefficients in the involved correlators. Unfortunately, quite a bit is known about the OPE coefficients of these operators. So here is a table with some references. So we need to look in the OPE with phi and with phi square, perturbatively in epsilon. And first you can see that in the right column here, there are these operators constructed out of 4 fields, which have order 1, at least in epsilon, somewhat decreasing size, but order 1 OPE coefficients in the phi square OPE. And kind of morally, to think of, there's a cost of creating an extra number of fields phi, which is the factor behind these extra powers of epsilon in the left column. And so the question mark here is a conjecture from this paper, which was really an auxiliary result from this paper. And then there are some missing entries. These powers in some missing entries I put in by the same logic that you would need to use some factors of epsilon to create phi to the 8 out of only 4 available fields.
Sorry, the conjecture was about the order of epsilon or the coefficient?
The order of epsilon would follow from the same argument that you need more powers of epsilon to create more fields. And the numerical number is the conjecture. It's a very precise conjecture.
Yeah, I can just say it's based on some positivity assumption in some crossing equation.
Oh yeah, we have the author here, so yeah.
That phase, some positivity will fail, so you have a little degeneracy, you have some constraints, and you can, like, if you assume that all the coefficients are positive, there's a unique solution. But in a 2-point function with a boundary where we do not know that all the coefficients are positive, it's believed. So if you buy that assumption, which is Rastelli's and company conjecture.
Was so precise.
Exactly. So Rastelli's and co-author, sorry, I shouldn't say that. Like, the conjecture of the first boundary bootstrap paper also implies down the line this number, but yeah. So it would be, in other words, if you disprove that, you also disprove positivity. And so that would be good.
So this is a very concrete thing to change.
So what can you learn by staring at this table? I mean, again, without making mathematically rigorous statements, it seems at least conceivable that the first operator missing, 5 to the 8, is indeed the one that has small OP coefficients. Both perturbatively as small epsilon, because they're suppressed by powers of epsilon. And even if you put epsilon to 1, this number is fairly small, numerically even smaller than this one, for instance. And indeed, the next operator here is somewhat captured by the study. Yeah?
Well, you got this numerical result, you got this EFM from minimizing the navigator function, right?
Yeah.
But if you make some other choice, would this operator phi to the 8 just appear?
So what you can do is you can take, okay, you could in principle just put points inside the island and try. We don't have the exact shape of the island, but you can try instead of the final point at the navigator, you can take some other points.
Yeah.
And some of our spectra have changed a little bit by that. Again, these first 4 operators are somewhat stable, and we've never really seen any signature of phi to the 8. But if you increase lambda, we expect it to be seen with smaller people.
Could you somehow force the bootstrap to give the second operator with the almost the general dimension?
I don't know. Probably you can do a lot of things. But
I guess maybe you could like first you for example go to like d is equal to 3.9 and then just scan the island and get like ton of events and find one that has this phi to the 8, and then just use this use the KKT condition to like keep track of d and then just go below.
What condition?
So basically this is this is like investigated by Nima. Right. So his method was like pick a specific EFM and then like change some parameter and then like each step just solve for the condition that gives you the EFM that gives you the EFM. And then this parameter that you change would be the dimension, just keep track of that one solution and go all the way to like d squared to 3 or even below.
Sounds good. Let's discuss.
Okay.
So yeah, another option would be to try to use Martin's rigorous bounds and try to put bounds along all these and see if you can actually, unless there is an operator here, actually
so
rigorously
so
rule it
if you
out.
would try to do that, the thing that you would see basically from this, so one thing you might think like, let's check where the forces would be there by demanding that there's only 5 operators and no below 9 or something. Well, it will just give a solution with only 4, that only requires the 4, namely the 4 that you're already seeing here. So in order to force that it needs to use this phi, you have to explore, some condition that apparently the spectrum only can obey.
Say that there's a minimal OP coefficient, which is like 0.1 times this or something.
Right. If you have OP coefficient, you can also say, well, I just want to include at least indeed such an OP configuration. That would be one way.
Okay. I'm already over time, so let me just flash the other results and then finish. So, okay, so we wanted to see if these mix. So we thought they would mix here, but then we went below 3, and instead it looks like they do get closer little bit below 3, and we saw this quite nice picture. So what can you do? You can rescale the axis a little bit, and it looks like this kind of expected parabola. So we can try to fit the conic section. Oh, it's not parabola, hyperbola. So we can try to fit the conic section, and the result looks like this. So this is fitted from only operators in this box, but it surprisingly seems to do somewhat well outside the box too. There's almost intersection here. I think it's a bit of a fluke. And you can write a more suggestive expression for this hyperbola as the determinant of a 2x2 matrix. And you get something that looks like what we had in the beginning of the talk. And now this parameter, this off-diagonal term x, which is half of the minimal separation distance, actually turned out to be numerically pretty small, even though we don't have like a 1/n expression to match with. Okay, that's...
Can you compute it by other filterative methods?
We were trying something and look at some... Actually now with Connor's paper in mind, we might revisit that argument. We tried to use some conformal perturbation theory to relate it to some OP coefficient lambda 5.6, 5.4, and then this box square 5.4. We thought that could be behind and we would get an estimate for this x, but it turned out to be 0 to leading order.
But there is no conformal perturbation theory for moving in d direction. There is only conformal perturbation theory for moving in coupling direction. That's the problem.
Yeah.
So you need to develop.
So then we need to start from the free theory in 3D. But this is very far from the free theory in 3D.
You need a new theory to develop this.
Yeah. Okay, so let me say in words the conclusions. So we did see some of what we expected to see. Some level repulsion. We investigated a little bit more the application of the external functional method and when the first operator that would go missing. And then there are some I want to mention a few future targets.
Sorry, I'm very confused.
Yeah.
Something basic. So we were saying before, if I understand correctly, that the bootstrap results for these operators of these dimensions cannot really be totally correct because, for example, there is a missing trajectory at 8, right? Is it true,
Yeah.
first of all? So there is error because there is even a curve of points missing around in a similar plot range.
So
to
this is
plot.
an approximation of the spectrum.
No,
I
so
also expect
I
it to shoot down a little bit.
8 shoots up, right? 8 is in 4 dimensions and it shoots. So by the time you get to 3, the guy which was 8 in
yeah, but the existence of 8 could repel the points, these first black points, making them be a bit smaller and then be such that when you get to this box, they annihilate and then get created again.
No, 8 shoots up. Look, the part
It's
of
not
the
even in
curve is in that plot, right? It lives above. So this problematic operator which is missing, it lives very much above all the points here.
Okay, well, let me ask it differently then. So how do we trust that this is a very small effect, right? In this matrix, as you are showing, the off-diagonal elements are very small. And for non-integer dimensions, we don't, if I understand correctly, we don't trust the bootstrap that much.
No, but
anyway,
the non-unitarity effects are even much smaller. There's some almost hierarchy
forget about
of
non-unitarity,
scales.
but even now, you are missing operators you are missing some operators relatively close by.
Yeah.
Even if you don't know where the trajectory goes, but imagine it's at 9 or something there. You're missing a full line of operators. How do you know that it doesn't affect this box and that doesn't change qualitatively the behavior of this box here?
Well, by rigor we can't be sure, but I think if some bad things would happen, we would see this as the spectrum maybe changing drastically when you go from one dimension to another.
So the question is, can the effect of an operator be weak enough that the EFM doesn't find it, but strong enough that it still affects what other operators the EFM finds?
Yeah, I guess.
It's very easy to guess what the correct picture is going to look like if you go to the plot where you have this missing operator. You have a previous plot where you have this missing operator. So you just have to say what's going to happen with the missing operator. What is your guess for what's going to happen with this missing operator?
Well, it better repel with 10, right?
Well, it will repel with 10, but what's going to happen?
Probably very tightly.
So there's going to be just some resolution of these curves.
But already here, there are other missing operators too. So already here, I expect it to be in the region of the EFM where it starts to putting operators a bit evenly spaced and not a true operator.
The point is that there's going to be a series of level repulsions, but the basic structure of the curves is not going to change. That's the basic.
Maybe we should move this discussion to the break. I wanted to, well, it's super interesting, but maybe...
If this above a certain delta is not real, then the question is why do we believe it's real below that delta?
If what is not real? The picture, yeah.
The picture. Above a certain delta, we know it's not real.
Yeah.
So Peter's question, I think, is why do we believe it's real below that delta, right?
So because someone had because I just gave a talk where we show that at least for the low-lying operators, the extremal functional method is highly accurate and can just basically make them into a rigorous bound. So there's clearly some transition from a region where the extremal functional method can really be trusted until we go into some higher region where they
do we understand that transition? Why it happens?
Well, I was trying trying to discuss this transition a little bit by discussing the first missing operator, right?
Just because of the size of the OP coefficient.
Yeah.
But very roughly.
And then after that it might capture some operator, but already above the first missing operator, I would stop trusting it.
You're also including the 5 squared 4-point function, right?
Yes.
And the OP coefficient of that operator in that correlation function, what is it?
Well, we had it was conjecture at least or epsilon 4.
Ah.
Okay, the final point I want to say before we continue, before we finish.
I think you can prove there has to be at least epsilon to the 4. That's big.
We don't know the coefficient.
Yeah, we don't know the coefficient. It might be large. I want to make kind of a more general take-home message because now we keep studying the Ising CFT all the way, and so if you're interested in some more complicated theory, QD3 or 5 to the 4 with very complicated symmetry group, it's typically hard to find this in a bootstrap signature, and you might need to put many gaps. So my proposal is to start in some parameter, maybe epsilon expansion, maybe 1/n expansion, and use the perturbative spectrum to put a few educated guesses on the gaps in order to try to see a feature. So maybe you put a gap here for the third operator, and then you do a study at finite epsilon, and then you see, oh, maybe it was very close to your gap. Then you re-evaluate your gaps and take it lower, or if you find it higher up, you can re-evaluate your gaps and take them higher. And then hopefully you'll be able to track down a theory from perturbation theory to the region of physical interest. And you can even use the spectrum extraction as a way to monitor this, like how well is the spectrum looking continuous all the way down to the finite region? Then probably your perturbative theory and your bootstrap feature are related. And if you see some abrupt change, you need to reconsider your gaps. That's kind of a more general take-home message I wanted to give. But thank you very much for listening and the discussion.
Please, Slav.
I just wanted to mention about your last proposal that there was a paper by Singlets.
Yes, good.
Who did precisely this moving in D and moving in N.
And otherwise, I completely agree with this strategy. It's a very promising strategy, and in fact, we are doing something like this for OAN cross-2 model, where there is a whole interesting geometry in this ND space with Martin, Benoit, and Balt. So I think indeed in the old days, people were often restricted by the computer power to like studying just D equals 3 or particular value of n, and it looked difficult to move in the space. But now with the navigator function, it's really easy to explore this whole ND space geometry, and we should do more of it.
Any further questions?
I thought in DSC's paper he actually had kind of like a more detailed model for how you could get a Hamiltonian like this, and then he diagonalized it and you see that there's level repulsion. Does that give you any sense for, I forget if that was in general D or if you only did that in D equals 3?
So his study was in D equals 3, but for operators with increasing spin. So following down the spin families, and if you do it naively without some level repulsion, you get the worst match than if you take this into account.
And if you take, if you dial D, do you see these operators come very close to crossing in the right place? Do you know? Did you ever try?
If you dial what?
Well, if that was just in D equals, so the operators look like they're this crossing that you were showing, almost level crossing, is in D equals 2.8 or something. So is that, does the extrapolation of D also work? And does that give you a sense of why they're coming so close?
Okay. We talked about you.
I haven't, yeah, I haven't really thought about continuing in D. But the, I mean, you could certainly follow the strategy I followed, keeping D as an additional parameter, and it would give you some 2x2 matrix that depends on D, that you could then try to diagonalize. But yeah, I don't know what it looks like when you only move in the D direction and not the J direction. I mean, yeah, I can say like the strategy that leads to the matrix is just in the inversion formula, you have some quantity on the left-hand side, which is some sum of operators you're interested in, and on the right-hand side you have an infinite sum over operators in the other channel. So you want to match the right-hand side to the left-hand side, and the matrix gives you a better match than than a more naive approach. And I think that this thing of matching the two channels and you being able to do a better job with the matrix is probably still true in D dimensions.
One reason I was asking this is if your results, the 2 points, the two lines come surprisingly close. So the level of sturdiness is sort of in your results, the two lines come surprisingly close. The level of repulsion is surprisingly small, and that sort of seems like something that might have an explanation.
Well, yeah, let me comment on that.
Okay.
So before we started our study, we genuinely didn't know what to expect. I mean, we thought it would happen here, but we generally didn't have any expectation of how big this X would be. And if you have X big enough, you're not going to see any nice feature at all. So in a way, this estimate of X is a result of our study. Thinking a little bit more about it, it might mean that the epsilon expansion in a way works better than expected, and that people like to call the 3D Ising strongly coupled, but perhaps it's not as strongly coupled as you think. Perhaps just working with the epsilon expansion you get a good estimate, and that might explain why also the critical exponents and everything work well in 3D, and maybe you can think of this off-diagonal X as some measure on how strongly coupled the theory is, but this is pure speculations.
I mean, the epsilon expansion worked well, we have known it forever, right?
For the first few operators, yes. Yeah.
Can I ask a general question? So, I just want to understand the underlying principle a bit better at finding epsilon. Is there some way to think about this like in some kind of categorical sense, like Slava discussed for the OM, you put N, where you define some notion of OPE through abstract property of representation theory of the conformal group or concurrent group? Can this be made rigorous?
Well, can it be made rigorous? Then you should go to Slava's paper. But in general, even if you continue both D and N, they were discussing N, but the story is more or less exactly the same in continuing in D. So you need to, so firstly you need to go from SOD to OD. But this is a parity respecting theory, so if you combine parity and SOD, you get OD. And irreps of OD you can naively continue, or you can formalize it. So this seems to be the underlying fact that you can do these continuations. Then you're going to have a lot of representations that identically vanish in 3D or even in 4D, which are actually those behind these non-unitary operators. And then how much you want to formalize it, I think, depends on how much of a mathematician you are. And Slava might be more of a mathematician than me. I'm quite happy to look at these pictures.
I guess I mostly want to understand what, let's say, the associativity of OPE means in that context.
Can you define associativity of non-PE in the categorical framework?
There are some subtleties here, but I'm looking at Miguel.
No, you are good. I'm fine. We have time. Hold on, I'll give you the back.
You can make all this categorical machine work also for OD. The reason why I consider this OD case more complicated than say OM case is that we don't know. I mean, at the level of CFT and yeah, we don't really know what is the non-perturbative meaning of this OD symmetry for spatial symmetry. While for N symmetry there is some reformulation, non-determinate reformulation of what it means in terms of loop models. And so you could just, it's not just a mathematical machine, even though you often seem to believe so, but you can really take a O with N equal 3.5 model and you can actually Monte Carlo simulate it, so it's very concrete, it's not mathematical at all. While we don't know how to Monte Carlo simulate directly Ising model in 3.5 dimensions. We can talk about it as an analytic continuation, we can discuss whether this analytic continuation makes sense or not, we can compute using the Bootstrap, but we don't have a first principle probabilistic approach to it. So I think that's the main difference between that's why I consider that this is still a novel problem.
Okay, guys, we can discuss in the afternoon much more.
Yeah.
So let's thank both speakers. Let me just briefly tell you how it proceeds. So we now walk across the street to the place where we are lunch. In this place, there is a big tent